In the government's latest response,
You must stay at home.
Master of the house, doling out the charm.
It's very important that everyone
know that you are not alone.
G'day chemists. So in this video, we're going to look at kind of the language of chemistry, right? Like how do we refer to different compounds, different molecules, different elements? And we do this using a specific language, just like we would with any form of communication, which is fairly universal across the planet anyway. I mean, universal, but it's like the American World Series of baseball, We speak it. We use it. Scientists everywhere across the globe use the same language. And that is the chemical formula. So we're not actually talking about the equation, which is these reactants go into these products. We're not talking about that. We're talking about like those individual units. So if you had hydrogen gas plus water plus oxygen give you water, here we're looking at just the H2, just the O2, or just the water, like that individual chemical, whether it's an element, compound, molecule, and the formula for that. And we're going to look at different representations that mean different things, and they're all useful in different ways. So this is your vocabulary. If I could just get you to pause the video here, write this down, and that way you'll be able to refer back to it as we move through the video. That'll make your life so much easier. All right, so we'll start off with an ionic compound, and this is only so we can get to what a formula unit is. But an ionic compound, it's like a type of chemical compound made of cations, positively charged ions, or positively charged ions, and anions, which are negatively charged ions. They transfer electrons. So what elements transfer electrons, that makes them ions. They get really attractive to each other, and they just boom, stick together. And that's through electrostatic forces, and it's kind of fun and interesting, and these are really strong bonds. They really have a high melting point. Boiling points, usually solids at room temperatures. Examples of these are, and this is the fun part, sodium chloride, calcium chloride, or magnesium oxide. All right, now, one of the fun things is that we represent these in a formula unit, and this is the lowest. So instead of these don't have a chemical, well, they have a chemical formula. They don't have a molecular formula. They have a formula unit. So it's the lowest whole number ratio of ions in an ionic compound. For example, here we have sodium chloride. The sodium chloride in this element here, in this ionic compound, will have millions of chlorides, millions of sodiums in a recurring lattice. This means it's a 3D structure that just repeats over and over and over and over, right? So we use a formula unit to describe the lowest simple ratio of that. For example, for every single sodium, there is a chloride, right? And that's how it works, right? They are a 1-to-1 in sodium chloride. And so we use that. So instead of calling it a single molecule, it's an ionic compound, but we use a formula unit. So that's the smallest ratio. Essentially, it's an empirical formula, which we'll talk about in a sec. So for example, sodium chloride, calcium chloride 2, that should be a subscript there. Calcium chloride 2, or calcium chloride, but with a little CaCl2, that means for every calcium, there are 2 chlorides coming off, and that repeats in a 3D structure. Magnesium oxide, it's MgO, and that means for every magnesium, there is a single oxygen. And that gives us all sorts of weird fun shapes, right? Like for our crystals, which just for funs are also, they tend to be seen when it expands into its biggest shape, like that's usually representative of its crystal. We also have molecular formula. So a molecular formula is a representation of the actual number of atoms of each element in a molecule. So it indicates these and can be used to indicate the arrangement. It can be the same as the empirical formula, like the formula unit of a molecule. We don't call them formula units in molecules, but really that's what it is. It can be the same as that, or it can be larger. It can never really be less. It provides more information than the empirical formula, and it can be used again, particularly in organic compounds, to work out the exact ratio. Over here, we have glucose. Glucose is one of the more important molecules you'll ever learn about, and we have 6 carbons, and makes this nice little ring with a little thing off the side here, and another one joins that, and that's how you get your sucrose. And we have these hydrogens, and we have these oxygens around it. If you were to add them up, I wonder why these hydrogens are different shapes. That's no good. Anyway, whatever. If you were to add these up, you would have 6 carbons, 12 hydrogens, and 6 oxygens. Another molecule, and you can see that can be busted down into a smaller ratio. We'll deal with that in a sec. However, water, which is H2O, that's also the molecular formula, but that's as small as that can get. And then we have octane at C8H18, which leads us to our next type, right? The empirical formula. It's cool. It's fun. It's fun to work out, and we'll do that in our next video. So the empirical formula is a representation of the simplest whole number ratio of this molecule. I'm pointing at, you can't see, this molecule right here. It does not necessarily, although it can, represent the actual number of atoms of each type, but it does keep them in the same proportion that they would be. It can be the same as or smaller than the molecular formula, can't be larger. Provides basic information such as what's there, but not how they're put together. So for some examples would be, for carbon here, right? If there are for glucose, if there are 6 carbons, 12 hydrogens, and 6 oxygens, that means it's going to be 1 carbon for every 2 hydrogens for every 1 oxygen. And that's actually the ratio for all carbohydrates. So if we were to break this element, this is something we can do quite easily in lab. If we were to break this compound down into its constituent components and we were to work out what percentages of each element was there, we could at least tell pretty quickly that this is a carbohydrate, not an oil, and so, so it's really useful there. That was a lot. If you have any questions, put them in the comments below, and we'll get back to you as quick as we can. Hit like and subscribe, I suppose, and yeah, we'll catch you next time. Bye now.